Okay, so let's talk about the bane of my existence is why they use negative electron volts, but they did, but you need to be able to handle this situation. I promise you, on the test you're going to have, I'm not going to give you negative electron volts, okay? But it's the same concept, it's just like from a different perspective of where you're defining your energy levels to be. So, in this situation, and part of this is, if you read the instructions, it says you have to assign principal energy levels, okay? So, in this situation, what they're defining as like zero as being like an infinite distance for the electron to be from the nucleus. So then, if you take that electron and you move it closer and closer and closer to the nucleus, then you're building up that energy, okay? But it's negative because of the fact that you're working in the opposite direction that the electron wants to go. So that's why that's defined as a negative value, because the electron is attracted to the nucleus. You can make the argument that that's more mathematically and physically realistic, but it's annoying. So this is why that -6 value is actually defined as the first energy level, because that would have been the one that was closest to the nucleus, okay? And that's why that's defined as n equals 1. And then n equals 2 is -3, and 3 is -1. Now, if you had been given positive electron volts, then the 1 would have been the one that was closest to it, because now you're viewing it from the opposite perspective, that you're taking the electron that's at the nucleus and you're pushing it away from the nucleus. And that's why, so if it had been positive values, n would have been 1, 3 would have been 2, and n equals 3 would have been that +6 value, okay? It's the same idea in terms of energy transformations. That's the main thing. So, one of the important things you need to know is the difference between an absorption spectrum and an emission spectrum. So which one will have more lines in it? The emission spectrum or the absorption spectrum? Emission. Emission always has more lines because on an emission spectrum like this, I can go from here to here to here to here to here, okay? So I have much more different ways that this thing can return back to this ground state. Whereas on an absorption spectrum, you can only go from the ground level up. So I can only go from here, I can go to there, I can go to there. So if you're given a comparison, your emission spectrum is more complex than your absorption spectrum. Okay, so, and some of you, when you, on that assignment that I just gave back, and you want to figure out, hey, what wavelengths you can see. And this is one of the most important things, this is a broad idea that you need to understand, is that there is no way for us to actually see the movement of electrons. It isn't like we can take it and put a hydrogen atom underneath the microscope and we'll watch the electron go around, which right away you can't do because of the Heisenberg uncertainty principle. Because by the very act of seeing it, you have to hit it with such a high energy photon that it completely knocks it out of its orbit and then you don't know where it is afterwards. So the act of observing it screws it up. So we can't see it, first of all. And second of all, when it goes from that transition from that first energy level to the second energy level, and this is where it gets weird on any number of levels, like the electron does not exist. So if you were riding the quantum elevator, you would get in on the first floor. And let's say you wanted to go to the 4th floor. You would get in on the first floor, a certain amount of energy would be given to you. You would cease to exist until you reappeared on the 4th floor, okay? It isn't like you would travel, I'm going to travel up to the 2nd floor and then the 3rd floor, and then I'll stop on the 4th floor. Not happening. Like, you do not exist in between those two states. There is no transition. But that's also why you get emission spectrums, because of the fact that those electrons can only absorb and emit certain amounts of light. So this is the big picture. So if you know the energy of the light that's being kicked out, you know the difference between the energy levels. Oh, red light, cool. That's a long wavelength, relatively small amount of energy. Nice. Violet light on the other end of the spectrum, shorter wavelength, higher frequency, more energy. This is why sunsets are red. Because, and you go, what does that have to do with anything? Well, so if you look at, here's the Earth, and here's sunlight coming through. Well, right now, if at noon, okay, the sunlight's coming straight on, straight through, boom. If you're at sunrise or sunset, then for you to see that light, it has to travel through more of our atmosphere. The longer wavelength red light, because it's lower energy, makes it through the dust and particles in our atmosphere easier than the higher energy particles do. So this is why sunsets and sunrises, even in terms of the moon, tends to have a reddish orangish color to it, because those lights make it through the atmosphere and don't get scattered like the higher energy particles do. So back to our story. So you've got these transition energy levels. So if you're asked to determine the emission spectrum, okay, your emission spectrum, you have to take all the different possibilities into account. You can go from 1 to 3, that would be 2 electron volts. You can go from 3 to 6, that would be 3 electron volts. You can go to 1 to 6, that would be 5 electron volts, okay? So, yeah, especially if you have like multiple energy levels, you have to take into account every possible permutation, because on the emission spectrum, they can stop on the way down. Absorption spectrums, you can't. So, on part B, where it says calculate wavelengths associated with each possible transition, you should have 3 of them, basically ranging from 250 up to 620. So which one of those is the biggest energy jump? The shortest wavelength or the longest wavelength? Shortest wavelength, which would be at 250, which is that 5 electron volt transition. Okay? That's the that's the biggest energy difference. That's the energy of the light that's being kicked out. Then when you get to C, the atom is the ground state, electron traveling at 1.3 collides with it. Can the electron excite the atom to the state of n equals 2? So this gets a little bit wonky in terms of how they're saying this. Technically, it's just going to be a single electron that's going to make this transition. But what they're saying is that they're treating the atom as kind of like one energy particle. Okay, so see you, Will. Good luck. So you got to find the energy associated with that electron, and that's going to be 4.8 electron volts. And again, you have to look in joules or electron volts. Pick one, okay? I don't care. I change it into electron volts. And then on that transition, can it excite the atom to the n equals 2 state? So if you go in from 1 to 2 and you look at that energy that's involved, the energy of that electron is more than that transition, which is that 3 electron volt transition. Therefore, it can make that happen. So that answer to C is yes, because of the fact that it has more than that amount of energy. And then another electron from the ground, the atom then decays back to the ground state by emitting a photon. Calculate the energy of the emitted photon. And that should be like 4.8 times 10 to the negative 19th. And then it says in which region of the magnetic spectrum. So in round numbers, okay, your visible spectrum is roughly 400 nanometers to about 750 nanometers. So if you do that math, it's at 413, and so therefore it would be in the visible light spectrum. Do not memorize this visible light spectrum. If you need that on the test, I will give that to you, okay? It's general knowledge, hey, what's the wavelength of visible light? If you happen to be playing Trivial Pursuit or something like that, you randomly know that answer. Okay, so flip that over and look at question 7. It's got that 2012 and it starts off with the momentum of a particular proton. So try that one. Danny, stop you under camera.